Hello everyone, I am Dr Sunil. Today in this video lecture I will discuss about the method, and that method is Charpit's method. This is the most general method of solving partial differential equation of first order but of any degree. In this method I already told you that this is the general method of solving the equation of first order but of any degree, linear or non-linear, with two independent variables. For this, in this method, let me have the given relation, let me have given the equation in the form function of x, y, z, pq is equal to 0 given by the equation number 1. Since z is the function of two independent variables x and y, therefore we have another relation of the form dz is equal to p dx plus q dy is equal to dz is equal to p dx plus q dy, and that is denoted by the equation number 2. If we can find another relation between the variables x, y, z, p and q given by the equation number 3 other than given relation 1, such that when the values of p and q can be found out by solving the equation number 1 and 3, and after putting the values of p and q in the equation dz is equal to p dx plus q dy, and this becomes integrable, then solution of this will give the complete solution of the given differential equation by Charpit's method. So in this section we have to find another relation of the form, and which can be found out by taking its auxiliary equation. In order to find out the relation 3, we have to find out auxiliary equation of the form given by dp upon del f upon del x plus p del f upon del z is equal to dq upon del f upon del y plus q del f upon del z is equal to dx upon minus del f upon del p is equal to dy upon minus del f upon del q is equal to dz upon minus p del f upon del p minus q del f upon del q. And after solving taking any two fractions which gives the relation between the p and q are giving the values of p or q, we can find other values in the terms of p and q, and putting the values of p and q in the relation dz is equal to p dx plus q dy, which must be integrable, and after integration this result we can find the solution of the given differential equation, and this is the complete method of solving the partial differential equation by Charpit's method. So we complete understand this method, we take an examples. Now the question is that to solve 2x dash minus px square minus 2qxy plus pq is equal to 0 using Charpit's method. Now here we have the given differential equation. In this form we have to write the given differential equation as the equation number 1, that is the given by function of x, y, z, pq is equal to 2x z minus px square minus 2qxy plus pq is equal to 0. Therefore we can find differentiation of f with respect to x, differentiation of f with respect to y, differentiation of f with respect to z, differentiation of p with respect to p, differentiation of f with respect to q. Now Charpit's auxiliary equation is given by the equation df upon dq upon dx upon dy upon and dz upon. Now putting the values of all these derivatives here, we have the equation dp upon 2z minus 2qy is equal to dq upon q, dx upon x square minus q, dy upon 2xy minus p, and dz upon px square minus 2pq plus 2qxy. Now from above we have the fraction of the form where we have dq upon 0. dq upon 0 implies q is equal to constant. Now suppose q is equal to a, there is the constant. Now putting the values of q is equal to a, here we have to find values of p or q, a value of relation between the p and q by taking any two fractions. So we have taken here dq upon q is equal to 0, and this implies dq is equal to 0, and that implies q is equal to some constant, that is the a. Now putting the values of q is equal to a in the given equation 1, we have p is equal to 2x z minus ay upon x square minus a. Now putting these values of p and q in the equation dz is equal to p dx plus q dy, and we have here dz is equal to 2x z minus ay upon x square minus a dx or plus of a dy. Now to integrate this relation, we just write the equation in this form. We have taken a dy minus left hand side and divide by z minus ay. We have the relation dz minus a dy upon z minus ay is equal to 2x upon x square minus a dx. On integration this result, we have the relation of the form, and this will give the complete solution of the given partial differential equation, and that is the z minus ay is equal to bx square minus a, and this implies z is equal to ay plus bx square minus a. Here the integration is simple, so we can integrate and find out the solution of the equation. Now we take another problem to discuss this method more clear. So we have another problem. The equation is that we solve the equation p square plus q square y is equal to zq using Charpit's method. Now here we have the write the given equation in the form of function of x y z p q is equal to, so here we have p square plus q square y minus zq, and this is equal to 0, and this will be the given equation. Now Charpit's auxiliary equations are given in the form dp upon dq upon dx upon dy upon dz upon. Now we differentiate the given equation with respect to x, with respect to y, with respect to z, with respect to p, with respect to q, and find all the derivatives involved in the auxiliary equation. After calculating this derivative and putting in the equation, we have the result of the form dp upon minus pq, dq upon p square plus q square minus q square, dx upon 2 minus 2py, dy upon minus 2qy, and dz upon minus 2p square z minus 2q square plus qz. Here we take the relation of the form where we can integrate the relation. We are taking the first fraction and second fraction dp upon and dq upon, and solving we have dp upon minus q is equal to dq upon p. On integration this we have p dp plus q dq. On integration we have p square plus q square is equal to some constant of the form a square. So this gives the relation between the p and q, p square plus q square is equal to a square. Now using this result in the given equation, e square plus q square is equal to a square in the given equation, and after simplification we solve and simplify, we have the result of the form q is equal to a square y upon z. Now means we have to calculate the value of p and q in the terms of the other variables x, y and z. So we are putting the values of p square plus q square is equal to a square in the given equation. We have q is equal to a square y upon z, and similarly this implies that p is equal to a by z root z square minus a square y square. So after using this result, we have calculated the values of p and q in the terms of x and y, z, x, y and z. So we have p is equal to values and q is equal to values, and now putting these values p and q in the relation dz is equal to p dx plus q dy, we have dz is equal to a upon z, z square minus a square y square dx, and a square y z dy. And to integrate this result, we just write down the terms a square y upon z dy to the left hand side and divide by the relation z square minus a square y square. So left hand side becomes integrable and right hand side also becomes integrable, and on integration this result we have under root z square minus a square y is equal to ax plus some constant b, and after simplification and squaring both sides we have the relation of the form z square plus a square y square plus ax plus b whole square, and this gives the complete solution of the given partial differential equation by Charpit's method. Thank you to all of you.